Hello everyone. Today we are going to talk about one of the most fundamental and essential topics in computer graphics, which is polygon filling. So you might not think about it, but almost every digital image you see, from the app on your phone to video games to the user interface of your operating system, all relies on this concept. And we will be exploring the art of pixels and the algorithms that turn simple outlines into solid fill shapes. So what is polygon filling? At its simplest, it is the process of coloring in the inside of a shape. In computer graphics, we define a shape or polygon by its vertices and edges and basically connect the dot outline. So polygon filling is the algorithm that figures out which pixels inside that outline need to be colored in. It's what turns a simple wireframe into a solid blue button. And this is crucial for almost everything. It is the paint bucket tool in Photoshop. It's how vector graphics in programs look like Adobe Illustrator draw solid objects. And it's how 2D games render characters and backgrounds. And it's even a core part of how 3D models are rendered on your screen. And it's basically everywhere. So, when we want to fill a shape, there are two main ways to think about it. Firstly, there's the seed fill approach. This is the most intuitive method, and you start with a single pixel or a seed somewhere inside the shape. Then, like a drop of ink on paper, you expand outwards pixel by pixel until you are stopped by a boundary. So, we look at two examples of this. One is flat fill, and other is boundary fill. Secondly, there's the scan line fill approach, and this method is more structured and efficient. Instead of expanding from a point, it fills the shape horizontally, one row of pixels at a time, and much like an old dot matrix printer. And this is the algorithm that powers most professional graphic system, and we'll see why. Okay, so the core idea is simple. You want to replace an old color with a new color in the flat fill algorithm. Now imagine you have a large area drawn in white and you pick a seed pixel inside that white area. The algorithm checks its color. If it's the odd color, for example white, which is a basic color, and it changes it to the new color, for example say red. So then it recursively does the exact same thing for all of its neighbors, which is up, down, left, and right. This chain reaction continues until it hits the part where the pixel that is not the old color, and at that point it stops. And its main use case is exactly what you would think. It is a paint bucket tool, and where you click on a large single colored area to change its color. Now, how flat fill algorithm works for four connected points. So let's break down that into four steps. Firstly, we'll assume a four connected algorithm, meaning it only checks neighbors to the north, south, east, and west. So you pick your seed pixel, that's where you start, and you check. The algorithm asks, where is this pixel's color the one I'm supposed to replace or not? If the answer is yes, then it changes the pixel to the new fill color, and it then recalls the exact same function on all of its neighbors, repeating the process. If a neighbor is already the new color or if it's boundary color, the process for that branch stops. Next, we have boundary color. This is a very close cousin to flat fill, but with one key difference. Instead of replacing an interior color, this algorithm fills an area until it hits a specific boundary color. So it starts with a seed pixel and begins to expand, checking its neighbors, and it asks, is this neighbor the boundary color? If not, then is it a color I've already filled? If again a no, then okay, we'll paint it. And it then recursively checks that pixel's neighbors. This is perfect for filling a shape that you have drawn in with a clear single color outline like a black circle on a white canvas. Now, the difference is subtle, but it is very important. So, flat fill algorithm basically stops when it finds a pixel that is not the target interior color. And this is great for filling areas that might have a border made of many different colors, but it can leak or fail if the interior area you're trying to fill isn't all one solid color. Whereas in boundary fill, on the other hand, stops when it finds a pixel that is the boundary color. And this is great for well defined shapes, but it will fail completely and leak out if there is even a tiny one pixel gap in the border or if the border itself is multicolored. So both are seed fill algorithms, and they also share a common major weakness. Um, Also, the problem with seed fill is that stack overflow, because these algorithms are recursive, and every time they move to a neighbor, they add a new function call to the program's stack. And for a small shape, this is fine, but imagine trying to fill a high resolution and a complex polygon. The chain of recursive calls can become thousands of levels deep, and the process runs out of memory to store this chain, and therefore it crashes. So you can write them non-recursively using a queue, but they are still relatively slow and memory intensive for large complex shapes. They just aren't good fit for high performance graphics, and for that we need a better way. And that better way is scanline filling algorithm. This is the algorithm that powers most of your vector graphics software and is foundational concept for 3D rendering pipelines. It's fast, it's efficient, and avoids the problem of recursion entirely. The concept is completely different. It fills the polygon one horizontal row or scan line at a time. And for any given row of pixels, for example, say y equal to 10, the algorithm first finds all the points where the polygon's edges intersect that row. And then it sorts those intersection points by their x coordinates, that is from left to right. And finally, it just fills in the pixels between pairs of intersections. It fills from the first to the second intersection, from third to the fourth, and so on. Then it moves up to the next row, which is y equal to 11, and does it all over again. Now, what are the key concepts? So, to make this work efficiently, the algorithm uses a couple of clever data structures. Firstly, is an edge table, and this is the list of all the polygon edges sorted by which scanline they start on, and this make it easy to know when a new edge needs to be considered. Second, an active edge table where it is a key part, and it's a list of all the edges that are currently crossing the scan line you're working on. And as you move from one row to the next, this list is updated and new edges are added from the edge table, whereas old edges that have ended are removed. And it uses a rule called even odd rule, which is also known as parity check, and this is how it knows when to fill. For example, as it moves across the scan line, the first intersection it hits turns the fill mode on, and the second turns it off. The third turns it on again, and this perfectly handles complex self overlapping shapes. And the result is highly efficient and predictable algorithm, which is perfect for a professional graphics hardware. So let's summarize the three algorithms. The method, flood fill and boundary fill are both seed fill algorithms, which is typically recursive ones, whereas scanline is incremental and it is working row by row. And it's talk about the stopping conditions. Flood fill stops at any different color. Boundary fill stops at a specific boundary color, and scanline just stops at the end of the line segment it's drawing. To talk about the third comparison, flood fill is for paint bucket tools on bitmaps, and boundary fill is for simple defined borders, whereas scanline is a professional standard for all vector graphics. To talk about the efficiency of the three, this is the most important part, and flood fill and boundary fill are considered as low efficiency due to the high memory cost and the risk of stack overflow. But scanline is highly efficient. It's fast and it's predictable and it's scalable. And that's a high level overview of the main polygon filling algorithms. Each one has its place, from the simple and intuitive seed fills to the powerful and efficient scanline method that drives our modern graphics. Thank you and have a nice day.